So yeah, we have a full program, and almost all of the speakers are here, which is great because it's everybody's across the world, and some people are even attending. So yes, I don't want to take time away from the actual speakers, so we'll just follow the schedule here. We'll have 5 talks, and they're all going to be exciting. So I hope you all enjoy. So let me unshare. Oh. And Tushant, you can start.
All right, thank you. Is it?
It's not full screen. But other than that.
Can you see my screen properly?
Yeah, now it's working.
All right, okay. So yeah, thank you all for coming. I'm Tushant, a grad student at University of Chicago, and I'll be talking about our work on explicit abelian lifts and quantum LDPC codes. The joint work with Fernando, Ryan, Pedro, and Madhur. So a one-slide summary is that we construct symmetric expanders using de-randomized group-based lifts. So in this talk, I'll talk about why they are interesting and how exactly we will do that. So the outline is as follows. I'll introduce the problem and state some motivation. Then I'll define these group-based lifts and quickly give a history, and then mention it with an application and conclude with some open problems. So I mentioned 2 nice graph properties. So the first is expansion. You might all be familiar with it. It's a notion that captures how well connected your graph is. So for example, how quickly random walks mix on your graph. And on the other hand, we have the notion of symmetry. So this graph intuitively has a cyclic symmetry. And more formally, we say that Z6 can be embedded in the automorphism group of the graph, which means that this is just the group of all isomorphisms of the graph, right? So if this occurs, we say that the graph has symmetries of Z6. All right. So individually, these questions have been well studied. So by now we know a lot of explicit constructions of sparse expander graphs. So constant degree expander graphs that are very well connected. And we have classical results, which says that for any finite group H, you can explicitly come up with a graph whose automorphism group is exactly the group H, right? So individually, we kind of know the answer to these questions. And the question that we ask is, can we have both simultaneously? Right? So now, why would we do that? So let's look at a couple reasons why I'm interested in this problem. And our motivation comes from a recent collection of results on quantum LDPC codes. So, a generic result is that if you take 2 codes which have a symmetry of a certain group H, then you can combine them in using a quotiented tensor product, which depends on the group, to come up with a quantum code, right? So this was first defined in this work of Hastings, High, and O'Donnell, and used also by Panteleev and Kalachev for the cyclic group. And this led to quantum codes whose distance preceded the known predecessors by quite a lot. And the recent breakthrough works of Panteleev, Kalachev, and Dinu, Revra, Livne, Lubotsky, and Moses show that you can construct constantly locally testable codes and good quantum LDPC codes via this kind of a construction. But now the group is a non-abelian matrix group, PSL12, right? So here it is key that you have both expansion in the graph, because these codes are constructed via the expander codes framework of Sipser and Spielman. So you need expansion to prove distance properties, and you need symmetries for the code to have symmetry and for such a product to even be defined. Okay. So this was our key motivation. Another interesting work on these lines is the recent work of Goldreich and Wigderson, which construct expander graphs which have trivial automorphism. So they have no non-trivial isomorphisms, and they use this to construct some lower bounds in property testing. So the key takeaway here is that while expansion is great, it's better. It can be much better to have control over the symmetries of the graph, right? So a bit more formally, we say that we want to answer the following question: for a given family of groups Hn, can you explicitly construct a family of expanders Gn such that Gn has symmetries of Hn, or Hn is the subgroup of the automorphism group of this? Throughout the talk, whenever I say explicitly, I mean polynomial time in the output, in the size of your output graph Gn, but there are stronger notions of explicitness that we have. Yeah, Yuval just mentioned there's another recent construction, and that also uses the same kind of product. Yeah, so now this is the key tool that we use, which is called a group-based lift. So lifting essentially takes a small graph G and lifts it up to a larger graph, G of S. So how do we do this? You take each vertex in a graph and replace it by L copies. So L is one of the parameters. And you replace every edge here by a perfect matching. Now this perfect matching is given by the signing function, which assigns to each edge a permutation. And when you have an edge comma L lift, we restrict these permutations to line this subgroup edge, right? So this signing function defines the lift of the graph. Therefore, we denote the lifted graph by G of S. Now, why is this a nice operation? So it has been classically studied in math, under the name of covering maps. But for us, it's important for the following reasons. You can explicitly characterize the spectrum of the lifted graph. So if you know the signing function, you can have a fairly explicit characterization of this lift, which is useful to prove expansion. It preserves degree from what we saw. And most importantly for us, if your group is abelian, then the lifted graph has a symmetry of edge, because edge acts on the L copies of a vertex. And because of abelian nature of the group, this translates to actually a graph morphism. All right. So let's look at a quick history of lifting in our CS context. So mostly people have looked at two lifts because, like I said, the degree is preserved. So you can construct an infinite tower of such lifts. So it is introduced by Bilou and Lineal, and the work on interlacing polynomials, and a recent very nice work of Mohanty, Oded, and Paredes, whose techniques we build on, have used this framework to construct expanders. But on the group-based sites, we don't really have a lot of explicit results. So Hall, Pudar, and Savin showed that the interlacing polynomial machinery of Marcus, Filmus, and Srinivasan can be generalized to certain non-abelian group lifts for some family of groups H. But they are specifically non-abelian. And the recent work of Agrawal, Chandrasekhar, and Kola and Madan showed that if you want to look at just the cyclic group, then random lifts of even exponential size are expanded. So this is far ahead. Going a lot from 2 lifts all the way to 2 to the n roughly. You can they are expanding, and they also complement this with the barrier result. So beyond a certain exponential, again in n, you cannot do much better, no matter what abelian group you take. And this is false for non-abelian groups. Non-abelian groups you can kind of lift arbitrarily high. All right. So now the question, more concrete question is, can we explicitly construct these lifts for larger lift sizes L? So can we do this for L lying from 3 all the way to this bound? So now I state our results. So we answer this question for a large range. So here L goes from 2 all the way to this impossibility barrier by ACKM. So the green region here is slightly sub-exponential. So 2 to the n to the some fixed constant. Or the region where it's exactly exponential, 2 to the theta. So we show that for large enough n and d, and this nice L, so L in this green region, we can explicitly construct expanding graphs that are ZL, L lifts. And here there's nothing special about the cyclic group. So like most results, you can generalize this to any abelian group. Transitivity is necessary for it to be connected, right? And here, some of these results are true for any degree, but in certain ranges, you really need to be degree to be high. All right. So one application of this is explicitly LDPC codes. So using the randomized constructions of Panteleev and Talachev, we can use our explicit expanders to convert their results to explicit constructions. So you can have good quasi-cyclic LDPC codes. So these are codes that are used a lot in practice. For example, the 5G spectrum uses these codes. And now you can have good codes where you have the freedom to choose your circulant sizes. So here the circulant size depends on how much, how large you can lift your parameter L. And on the quantum side, you can construct almost good quantum LDPC codes. So you have constant rate and almost linear distance of n by log n. And this is actually due to an improvement in the result of PK 21. So earlier you have weaker results. but now you can use this to construct almost good quantum LDPC codes. So yeah, that is all I have. There are a bunch of natural open problems here. You can try to make these constructions strongly explicit. You can try to fill in the gap that we have right now, maybe with a unified proof. So our proof technique is varies with the parameter L. So can you unify that? And can you generalize this to other interesting families of non-Abelian groups? So thank you for your time. Yeah, feel free to ask me questions.
Yeah, thanks. So any questions? So how many different constructions do you have? Like you mentioned, there are two ranges, and then maybe.
Yeah, so actually the construction, there are two of them. So let me correct. So here, the construction is kind of like there are two constructions, but the analysis is split into like three parts. So I can quickly show you one of the slides. Okay, can you see this slide?
Yeah.
Yeah, so here we have like three kind of regimes where we do analysis, and that leads to different kind of spectral bounds. So we have like almost Ramanujan in a certain range, like near Ramanujan or whatever that's called, and like just expansion in one of the other ranges. So the analysis varies, but the technique is unified here, but here the technique is different. Yeah, yeah, and also the de-randomization tools are kind of different, but yeah, broadly I'd say two.
Okay, so and any more questions? Okay, so let's virtually thank Tushant. Thank the name of us all. And Dinesh, now it's your turn.
Thanks, Yuval. Let me start sharing the screen. Okay. So I hope the screen is visible. So let me. So let's get started. So so thank you for joining. So this is joint work with Andrej, Yuval, Abi, and Akshay. And the title of the work is Bounded Indistinguishability for Simple Sources. And I'm Dinesh. So let's get started with some simple definitions. So let's say Z is a distribution over n-bit strings, and you say that Z is k-wise independent if every k coordinate looks uniform. So we have an example here. So let's say the distribution is A1, B1, A1 plus B1, A2, B2, A2 plus B2, and so on. Then this distribution is two-wise independent, and it's not three-wise independent because of these three dependents. Moving on, let's look at the second notion, which is the notion of k-wise indistinguishability. So you have a pair of distributions x and y is said to be supported over some n-bit strings, is said to be k-wise indistinguishable if every k coordinates are identically distributed. So here we have an example. So let's look at the previous distribution for n equal to 3 and take x to be the distribution conditioned on the a's summing to 0, and the second distribution to be the distribution z with a's summing to 1. So if you look at any two locations, either it is fresh random bits, or there is a fresh random bit that is getting added to, like where this plus is modulo 2 addition. So every two locations are going to look uniform, and for both x and y, and it will be two-wise indistinguishable, and it is not three-wise indistinguishable because you look at a1, a2, a3. For the first distribution, it will sum up to 0, and for the second one, it will be 1. So this could be generalized to sort of say that if you repeat it enough number of times, then you if you repeat it enough number of times, then you get an n-1 wise indistinguishable pair. So next, what we want to talk about is this nice result due to Braverman. So what did Braverman show? So suppose you have a circuit C, and you consider the experiment where you give it a k-wise independent distribution, and the other experiment where you give a uniform distribution, and you try to see if the circuit is able to tell these two distributions apart. And what Braverman showed is that if you look at any polylog-wise independent distribution, and if you look at any poly size AC0 circuit, the circuit will not be able to tell apart between these two distributions. And the measure that we're interested in is this distinguishing advantage. And think of this. So for the setting that we're considering, think of this advantage to be something which is vanishing. So motivated by certain applications in cryptography, Bogdanov, Ishai, and Viola asked if the same result holds if you replace independence by indistinguishability. So going ahead, they showed that this is not the case. And this follows by this result of Nizan and Segedi, who showed polynomials, who described a polynomial which agrees with OR on all the, it's close to OR on all the inputs. And you can by an LP duality argument, you can translate this for all statement to existence of these two distributions, which are square root and wise indistinguishable, but OR can distinguish them. So even a simple OR function can distinguish. So this tells that if you want to have a Braverman style theorem, it will require that you have a root and wise indistinguishability. So, so one difficulty, sort of an issue with this result, not an issue, but one sort of a drawback that one could say is that this distribution is somewhat hooked up. It's a bit artificial. So it's a bit. So then, what we ask in this work is it that Braverman's theorem hold because this distribution is somewhat complex? So does Braverman's theorem hold if you have simple sources, that is, if you insist that the sources can be sampled by given IAD source of IAD random bits. So some of the examples that we consider are local sources where each of the source bit is a function of constant many random bits. Linear sources where it's a linear function of the random bits. Quadratic sources where it's a quadratic function of the random bits. So having said this, let me just give a quick motivation as to where KYC indistinguishability arises in the cryptography. I did mention it arises in the cryptography. So it actually arises in the context of secret sharing. So let's say you have this one bit that you have to share with multiple parties and with many parties, and you want to make sure that only R of these parties could reconstruct the secret, while all other parties with K less than R doesn't learn anything about the secret. So here is a pair of K-wise indistinguishable distributions that come up. So if you take X to be the share of the secrets where the secret is 0 as one distribution, and the share of the secret when the secret is 1. So this pair, this pair of distributions is K-wise indistinguishable. So that's and sort of the indistinguishability part comes because of this requirement that no K parties get to learn about the secret. So what does this tell you? This tells you that if you can come up with a small circuit that is able to distinguish two K-wise indistinguishable, simple K-wise indistinguishable distributions, then the circuit would form the reconstruction, could be used for the reconstruction, and the fact that the distributions are simple gives you an easy way to distribute the secret. So this is if you can say that a Braverman style theorem does not hold. On the other hand, if you can indeed show that they hold, it has applications to leakage resilience and secure multi-party computation. So I won't go into the details, but yeah. So this is there are these nice applications. And having said this, so here are our results. So the first we show, so the table shows a set of sources and set of distinguishers that these sources distinguishers that are fooled by these sources. That is, they cannot tell apart any, for instance, an OR distinguisher cannot tell apart two K-wise indistinguishable simple sources where they are of constant degree or locality, and K is constant. And for depth 1 sources and for K is equal to log n, it can be shown that OR fools them, and this result could be shown to be tight, meaning for depth 2, this is not the case. And for the last two results, in fact, one of the, it suffices if one of the sources is simple. You don't need both of them to be simple. And in all these, think of the distinguishing advantage to be constant. And on the so this is, we call these to be the negative results. So since they don't give any secret sharing scheme, while you have we could show that there exists a simple source of which could be sampled by polynomials of polynomials of degree log n, which R can distinguish for k equal to root n, and so these are so they're efficiently sampleable. So so moving ahead, we also have a sort of an excuse for why we couldn't reach our target, where why couldn't we show for AC0 distinguishes a Bravers-Manstein theorem. So it turns out that so we could connect this question with several other related questions, and one of them turns out to tell that if Bravers-Manstein theorem holds, that is, you cannot distinguish two linear indistinguishable pair of sources by AC0 circuits, then that would mean that inner product cannot be computed by AC0 with leaf parity. So this is something that we do not know how to show with the current set of techniques. And this problem again did show up in the first session in Michael Ezra's talk. So and this is believed to be hard. So this sort of justifies why one would not sort of tells why we are unable to show it. So to conclude, let me just give a couple of open problems. So one of the results that we had with the R is that we could show like log n degree sources that that R can fool, log n degree simple sources which R can fool. And the natural question is this the best? Can you reduce a degree? We could show that you need non-constant. We can show that it's non-constant, but is log n indeed can you improve this log n? And there are several conjectures that we could show is related to this question of Bravers-Manstein theorem for indistinguishable sources, but we do not know if all of them are equivalent. So can we show that those are equivalent? That's one question. And the last one is there is no barrier that is known if you insist that if you have the sources to be local. And if you could show that AC0 there is an AC0 distinguisher that can distinguish local simple sources, then that would translate to a secret sharing scheme with local sharing and AC0 reconstruction. So that's all that I have to say. Thank you.
Okay, so let's thank Dinesh. And we have time for one quick question, if anybody has any.
Yeah, any questions?
On whether maybe a comment. Okay, well, if you think of something, then you can shoot Dinesh an email.
Yeah, sure.
So,
yeah, so then maybe. So Yuval, shall I stop sharing?
Yeah.
Yeah.
Can you please stop sharing, and then Marshall can choose the next speaker.
Sure.
And that's about space. About the space telescope. Yeah.
Okay, can you all see my slides?
Looks great.
Okay, excellent. Unfortunately, I have a menu blocking things, but okay. All right, so I'm going to tell you about randomness extraction from somewhat dependent sources, and this is joint work with Oded, Goldreich, and Tal Malkin. Oops. And so what is the problem of randomness extraction? So randomness extraction, we want to convert some weak natural source of entropy into a uniformly random bit string by applying a deterministic function to this natural source. Okay, randomness is undoubtedly very important in computation. So this but natural sources tend to look very different than random coin flips. And how do we model, this is probably all a review for most of you, but how do we model sort of what is a minimal assumption that we would like to make about these natural entropy sources, that they're unpredictable, that they have what's called min entropy. So a source has min entropy, at least k, if no outcome occurs with probability greater than 2 to the minus k. You can think of this as a worst case version of Shannon entropy. Okay, so there's two main branches of research. in the domain of randomness extraction, and one studies what's called seeded extractors. So here you're sort of assuming as little as possible about your source, just that it has some min entropy. Unfortunately, extracting from just one in this context is impossible. So in seeded extractors, you assume you have access to a uniformly random seed. So if our goal, though, is to turn weakly random natural sources into purely random bit strings, where are you going to get this random seed from in the first place? So the second line of research, or principal branch of research, there's other branches here that I'm not mentioning, is on what's called two-source extractors. So here you have two independent sources, each with min entropy. So this is great. You can have deterministic extractors here, but unfortunately, you have to make this independence assumption. And perhaps in certain situations, this may not be an appropriate assumption. So in this work, we ask this sort of natural question: can we relax this independence assumption? Okay, so it's a natural question. In fact, it's so natural that it was actually asked in the work that introduced this second branch of research into two-source extractors. So Penny Shore and Oded Goldreich in 1985 proved this negative result, which very informally said that if the two sources have even very small dependence, then extraction becomes impossible. And it seems like as a consequence of this theorem, no one sort of did any research in this direction for the past 40 years, even though it seems like a natural question. But you might be asking yourself, what do you mean by small dependence? So it's very clear what it means if two sources are independent, or if they're not independent. What does it mean for them to have small dependence? And sort of in this work, what we're doing is we're sort of looking at what it means for two sources to have small dependence systematically in the context of randomness extraction. Okay, so what we do is we introduce three different models of limited dependence between sources. So one we call bounded coordination, another we call bounded cross-influence, and another we call bounded mutual information. You can guess what some of these things might mean. And in all of these cases, all the three of these models, if t equals 0, just a sort of a sanity check, if t equals 0, the sources, you record the case of independent sources. And if t equals k, sort of the min entropy bound of the two sources, then you recover the case of two identical sources, or the single, which is effectively the single source case. And these models on the left, we have sort of the least general, model of limited dependence. And we have this sort of sequence of containment. So on the right, this bounded mutual information is sort of the most general. So we have these containments within where if you fix a t, then these containments hold. Or in the second case, between 1 and 2, it's actually an approximate containment. And we want to look at these models in the context of randomness extraction, or that's what I promised you. So we show that only in the first model can you have any hope of extracting randomness. The second and third models, there's no hope of extracting. And you might want to say, okay, let's give up. But instead, we look at a weaker notion, the notion of randomness condensers. So in a randomness condenser, imagine you have some huge natural source of entropy, but the entropy is like very sparsely distributed. So K, your min entropy bound, is much, much less than the size of the source. So what a condenser is again, a deterministic function, and it just sort of compresses this source down such that the min entropy of the output is very high, almost the length of the source. Okay. And we show that, in fact, in the second case, even though you can't extract, you can condense, and you can condense pretty well. So if T is pretty small, your condenser is pretty good. The min entropy bound is almost what you want. The loss of the condenser, the deficiency of the condenser, is T. And for the third model, we show that you can also condense, but qualitatively worse than in the second case. Sort of more technically, what this means is that the deficiency of the condenser is inversely proportional to its error. But I'm not going to go into any parameters in this talk. Instead, I want to just spend my remaining time telling you exactly what these models are. and refer you to the full paper to learn more about the actual results. So our first model is what we call t-coordinated sources. So we say that x and y, two sources, are t-coordinated if there exists this like coordinating random variable z, which has support size at most 2 to the t. So you can write down outputs of z in like as t-bit strings, and if I condition on any output of z, x and y become fully independent. Okay, this is the model again where you can extract. And an alternate view, an equivalent view of t-coordinated sources, we can imagine protocols, Alice and Bob, two-party protocols, where Alice and Bob, instead of trying to compute some function, they're trying to sample the sources. They have, Alice has private coins, Bob has private coins, and they're trying to sample two sources. And so the t-coordinated sources correspond to sources which can be generated by such protocols where Alice and Bob communicate at most t bits. Okay, so it has this sort of semantic, nice semantic interpretation. Okay, so that's the first model. The second model we call a cross-influence. And so here we're going to imagine that our sources are generated by these two functions, x and y, that take in uniformly random inputs. We'll think of like one input, like Rx is sort of being approximately local to X and Ry is local to Y. We want to bound the influence of Y on X and X on Y. So what do we mean by the influence here? What do we mean by the influence of Ry on X? We say that the influence of Ry on X is at most T if we fix any sort of particular Rx and Ry, and we then the probability that the output of this function x changes if we re-randomize Ry is bounded away from 1 by 2 to the minus t. Okay, so this is a definition of influence, sort of inspired by worst case notions of elsewhere. And t cross influence is just, we say that two sources have t cross influence if there exists these two generating functions, x and y, such that the influence of Ry on x plus the influence of Rx on y is at most t. Okay, so if we sum up the collective influence, is always at most t. Right, so whereas the first model sort of captured essentially where bounded coordination captured like potential influence of one source on the other, this is sort of capturing the actual influence of one source on the other. At least that's one interpretation. So our third model of bounded dependence probably needs no introduction, is T mutual information. So here we have the definition, mutual information. So the individual entropy, Shannon entropy of X plus the Shannon entropy of Y minus the Shannon entropy of the joint distribution. We say they have T mutual information if we can bound this quantity by T. And again, this model has this natural semantic interpretation. It corresponds to Alice and Bob generating protocols where they reveal at most T bits about their source to the other party. Okay, so I think that's about my time, unfortunately. So I'll leave you with this slide and a link on the bottom to the full version of the paper, which has a lot more details and intuition, including a fourth model called T-min entropy loss, and invite you to explore this more fully. Thanks.
So thanks, Marshall. Questions? Yeah.
Yeah. For the T-bounded coordination, are you just saying that conditioned on this, coordinating random variable, you have two independent sources, and then you just reduce to the independent source case, or okay?
Yes. So extraction is very easy because these sources are like convex combinations of independent sources. Is that what? Are you asking about the upper bound for how to extract from such a thing?
Right. I'm just clarifying.
Okay.
Right.
Yeah.
And for the other ones, are they reductions to other cases?
Oh, right. So all of our upper bounds are actually just by applying a generic two-source condenser, where like two independent source condenser to the model. And we show lower bounds that basically constructing some tailor-made condenser won't help you. So this is effectively optimal. So yeah, you just pick your favorite two-source extractor or two-source condenser and apply it, and that will be the best you can do. Assuming that it's already optimal, I guess, for a two-source case.
Thanks.
Yes. So your second model is the weakest model where this kind of argument works.
The third model you can also
model.
condense, but it's
Mhm.
qualitatively worse.
Okay.
Yeah, the deficiency of the condenser is much higher. And the deficiency of a condenser is like how far away the output's mean entropy is from sort of the optimal, which is the length of the output.
Okay. Any more questions?
Are there any
So-
natural open problems here that you wanted to solve?
Coming out of this, I think there aren't any natural open problems from this. I mean, you could consider other notions, I think, of limited dependence, perhaps, that might be interesting. Out of here, there's maybe some minor questions of tightening up the bounds, but yeah, I don't have any particularly compelling examples, unfortunately, on hand.
Okay, thank you.
Do you know that in the third model that you can condense better?
Well, yeah, we have a lower bound, so you can't condense better. Yeah, I guess, yeah. So so the open problems here reduce to, I guess, to constructing better two-source extractors. So by studying, in some sense, so if you just can focus on two-source extractors, you'll do better in all of these cases.
Okay, so thanks a lot. Can you please unshare your screen?
Oops.
Great, and now Jesse will talk to us about sampling.
All right, thank you. Let's see.
So,
Everyone can see this?
yeah, looks great.
Cool. All right, well, hi, I'm Jesse, and today I'll be talking about the space complexity of sampling. This is joint work with Ishai and David Zuckerman. So complexity theory studies the question, how many computational resources are required to complete a certain task? Now, traditionally, this task has been computing a Boolean function f. And in order to formalize the notion of a resource, what we usually do is fix some computational model, curly C, which will have some natural size parameter, which corresponds nicely to some resource. So then, given a so-called computer C in this computational class, we say that it computes the function f if, for every input string x, the output of C on x is the same thing as f of x, of course. Then, given this formalization, the question becomes, what is the smallest computer in our class that computes the function f? And we can call this question the complexity of computing. Now, in addition to computing a Boolean function f, another task that shows up a lot in computer science is sampling from a distribution Q. And so it's natural then to ask, how powerful are our favorite computational models for the alternative task of sampling? So inspired by two earlier works, in 2012, Viola launched a systematic study into this question. In order to formalize this question, what you do is you take one of your computational models from before and a computer C from that model. But now, instead of feeding it a fixed input string X, what you do is you feed it a uniformly random input string big X. Then we say that the computer C samples the distribution Q if the output of C on this uniform string is distributed identically to Q. And of course, the question then becomes, what is the smallest computer in our class that can sample this distribution? And we can call this the complexity of sampling or the complexity of distributions. So beyond these two specific questions, these two fields are generally interested in understanding the power of various computational models for the task of computing and the task of sampling. So in this work, we focus on the latter. So recently, there have been a lot of really exciting papers on the complexity of sampling. that help us, understand our classical models for this new task. But while significant progress has been made, results are still only known for a few computational models like AC0 circuits and communication protocols. And in particular, not much is known about the complexity of sampling with limited memory. So the goal of this work is to kind of fill in this gap and study the so-called space complexity of sampling. Now, before I can tell you our results, I need to answer two questions. So the first question is, what model should we use for sampling in limited memory? And then once we know that, we need to understand what are some interesting questions to ask about sampling with this model. So the model that we use for sampling in limited memory is just a classical model of read-once branching programs, which we slightly generalize in a natural way so that they can output multiple bits. And if you're not familiar with what an ROBP is, all you need to know now is that it has an important parameter called its width, W, which roughly corresponds to the number of bits of memory that this program can use to compute its function or sample its output distribution. And if you don't want to remember that, all you need to remember here is that more width means more memory, which means more power. So that's our model, ROBPs. And so now we can ask what questions are interesting to ask about sampling with ROBPs. So in order to figure this out, we'll revisit a paradigm that appears in a lot of these papers on the complexity of sampling, which is that sampling is actually easier than computing. So what we mean by this is that there are actually functions f such that it's hard to compute the output of f on every single input x, but its output distribution can be very easy to sample. So as kind of a conditional example, you could think of taking f as the inverse of a one-way permutation. So by definition of one-way, f will be extremely hard to compute, but by definition of permutation, its output will be uniform, which is extremely easy to sample. So there are explicit examples as well. So given this paradigm, it turns out that sampling lower bounds are more challenging than classical lower bounds to obtain. And it's been argued that pursuing sampling lower bounds could yield new techniques and surprising applications. So our goal in this work is to obtain sampling lower bounds against ROBPs. So we have two main results in this direction. So I'll introduce each and go into a little bit of detail on each of them. So our first result is strong sampling lower bounds against a natural explicit distribution for ROBPs. So if we'd like to obtain sampling lower bounds against ROBPs, the first question is, can we just find a distribution that cannot be sampled? So one of the first computational models in which this was studied was AC0 circuits. So to make things a little more explicit, the question becomes, can we find the distribution Q such that the output distribution of any AC0 circuit is not exactly Q? So this turns out to be actually trivial. And so in 2012, Viola introduced the more interesting challenge of, can we find a distribution that cannot even approximately be sampled by AC0 circuits? So by approximately, we mean that the output distribution of any AC0 circuit should be far from the distribution Q in terms of statistical distance. So later in 2012, Lovett and Viola answered this question by providing a very natural distribution Q with very strong sampling lower bounds against AC0 circuits, namely sampling lower bounds that are polynomially close to 1. And then later in 2012, Beck and Pagliazzo and Lovett improved this sampling lower bound to be exponentially close to 1. And it's for the same distribution Q. And this distribution Q turns out to be very natural. It's just a uniform distribution over a good code. So by good code, we mean that an error correcting code that has linear distance and linear dimension. So on the other hand, turns out that good codes are extremely easy to sample using communication protocols. And so a natural question then is, where do ROBPs fit in this picture? And in particular, are good codes hard to sample with ROBP? So our first main result answers this question, and it says yes. So it says that for any good code Q and any ROBP of width, say 2 to the 0.01 n, the output distribution of that ROBP is exponentially far from that good code. And using a known connection by Viola, we automatically obtain these data structure lower bounds against storing code words. So that's our first main result. Our second main result is the so-called direct product theorem for sampling with ROBPs. So in order to introduce what a direct product theorem is, a question that we're interested in is the following. So suppose that we have a distribution that is a little bit hard to sample for some computational model. Then the question is, can we use it to build another distribution that is extremely hard to sample for that same model? And the reason why this is, and furthermore, we'd like Q star, the distribution we build, to be just a little more complicated than Q. And the reason why this is interesting is because if we can answer this question positively, then we can use it to strengthen separations between complexity classes for the task of sampling. So the answer to this question is exactly a direct product theorem. So direct product theorems are well studied for the task of computing. And here they roughly say the following. So suppose that you have a function that's hard to compute for some computational model, then you can use it to build a function f cross t that is very hard to compute for the same model. And f cross t is just defined by taking its input, chopping it up into t parts, and then applying the hard function f to each part. And one example of a direct product theorem like this that's known for computing is Yao's XOR lemma. So for the task of sampling, a direct product theorem might be defined as follows. So suppose that you have some distribution Q that's hard to sample for the class curly C. Then we'd like to build a distribution Q cross T that's very hard to sample for the same class, where naturally we define Q cross T to just consist of T independent copies of Q concatenated together. Now, it turns out that no direct product theorems are actually known for the task of sampling. And so our second question here is, can we establish a direct product theorem for this task, and specifically for ROBP, since we're studying the limited memory model. So our second main result answers this question in the positive, and it shows that for any ROBP of width W, if its output distribution is delta far from Q, then for any ROBP of width W, its output distribution is exponentially far from Q cross T. So that's our second main result. So kind of just to conclude here, we proved two main results. So our first main result is a sampling lower bound against good codes. So previously, this was only known for AC0 circuits, and the sampling lower bounds that were known were extremely strong. And on the other hand, good codes are very easy to sample with communication protocols. And we show that ROBPs behave a little more like AC0 circuits than communication protocols in this setting, in the sense that they have a really hard time sampling good codes. And again, using the connection of viola, both of these results have applications in data structure lower bounds. So in the context of direct product theorems, nothing was previously known for the task of sampling. And we established kind of the first direct product theorem for this task, and we established it for ROBP. And one cool thing about our proof is that one of the main ingredients gives a simple new proof of another sampling lower bound obtained for communication protocol, sampling disjoint sets. So because this is a super new area, there are a lot of interesting open problems. So one problem is maybe, can we establish direct product theorems for other computational models besides ROBPs? Another thing is, can we kind of extend our sampling lower bounds to work for read K branching programs? And finally, it'd be interesting to exhibit distributions that demonstrate separations between the power of AC0 circuits and ROBPs for the task of sampling. So it's really easy to find a distribution you could sample in AC0 that you can't sample with ROBPs, but it's quite hard to show the other way around. And we don't know how to do it yet, but some advances in extractors would answer this question for us. So that concludes my talk. Thanks for listening. And I'm happy to take any questions.
Yeah, thanks. So we have time for maybe one quick question.
Yeah, I have a question. You mentioned that communication protocols can sample good codes. Can you say how this is done?
Okay. So I guess the standard model, or at least by Booth and Watson for communication protocols, is Alice and Bob each have their own private randomness, and they could communicate. And at the end, each one has to output a part of the distribution. So what you could do is they could just not communicate at all, and Alice can use all of her randomness to just output a code with like 0.01 distance and rate, or rate and relative distance.
So Bob does nothing?
Yeah, so Bob does nothing, and Alice just outputs the code herself, because it's still good even if it has rate and relative distance less than half.
Oh, I see. Okay. So it's okay. So I mean, all right.
Yeah.
It seems like a bit of a cheat. Like maybe if you're looking for a specific code, then this one for.
Yeah, I agree.
Yeah, also the rate. You can ask more from the rate, but yeah, I mean, I get what you're saying. The one is to be careful about these things.
Yeah, I guess there exists a good code that they can sample, whereas ROBPs and AC0 circuits cannot sample any good code. I guess that's the main distinction.
Right.
Yeah.
Thanks.
Yeah. Yep,
Okay,
thanks.
so we're a bit over time. So if there are any more questions, then you can take them offline. So thanks again. Can you
Thank you.
please? So Huang, you're last.
Okay, so can you see my screen?
But we can't see the full screen. No, yeah, now it's working.
Okay,
Great.
okay. Hello everyone. I am Huang Ta. Today I'm going to present to you our work about the laser Cochlear Physics from the combinatorial degeneration. This is joint work with Madhur, Christian, Omar Fazi, and Jigun Jaram. In this paper, we construct a special combinatorial object called the Cochlear Physics, which is motivated by a central problem in the communication complexity. Namely, we consider multi-party communication complexity on the number on the fourth model. The Cochlear Physics has studied in the some work of the Shellman, Dina, Pitasi, Viola, and the Carver. Namely, in the work of Lina and Shellman, they construct the large Cochlear Physics in the integer grid by designing efficient and NOF communication protocols. In our paper, we take a different approach. Namely, we consider the Cochlear Physics on the finite field setting and introduce in this area the method of the combinatorial degeneration. So what are the Cochlear Physics? A Cochlear is a triple point of the form xy, x plus lambda y, and xy plus lambda, which lambda is a non-zero. There are many various settings of the Cochlear in the integer grid and by n, or grid over the finite group, the G times G. A subset of the point in the G times D is Cochlear free if it does not contain 3 points of the Cochlear. We denote the R of G be the size of lattice Cochlear Physics in the grid G times G. In our paper, we study on Cochlear Physics on the finite field FPN. Namely, we show that for the largest Cochlear Physics in the F2N is at least 3.39 power n, which compared with the 2.S2 power n provided by the work of the Lina, Pitasi, and Sharman in the 2018. And for the R of the F3N, we shown that it's at least 7 power n, which compared with the 6.6 power n, which constructing by using the error construction for the capset problem. Our motivation come from the deterministic communication protocol on the EVA function on the number on the fourth model in the multi-party communication complexity. In the some work of Chandra, Bush, and Litton in the 1983, and in the work of Lina, Pitasi, and Sharman in the 2018, they show that any large Cochlear Physics can be used to the provide a communication protocol for the EVA function. That means any good low bound for the large Cochlear Physics, we can make a good protocol for the EVA function. Our methods can be summarized as follows. The first, we describe the Cochlear Physics problem as a hypergraph. Namely, we construct a hypergraph with the Cochlear equivalent to the axis of the hypergraph, and the Cochlear Physics is equivalent to the independent set in this hypergraph. The hypergraph has the power structure. Then we introduce the general method for the constructing large independent set in the hypergraph has the power structure for the combinatorial degeneration. Okay, we start with on the directed acyclic graph on the work of the Bidamon Mini in the 1985 for any directed acyclic graph with a vertex V. Then on the n copy of this graph, we can construct independent set of psi v power n minus small o n. The idea as follows: we consider the agent-symmetric of this graph, and in this agent-symmetric we put the all diagonal entry equal to 1. Because the graph is acyclic, therefore the agency tensor agent-symmetric is the upper triangular matrix. Then if we take the n tensor power of the agent-symmetric, it is the agent-symmetric of the n copy of this graph. Because the n tensor power of agent-symmetric also the upper triangular matrix, therefore if we take the submatrix indexed by the uniform n tuple, we can obtain the identity matrix. Therefore we can construct a psi of independent set on the n copy of this graph has the psi equal to psi of uniform n tuple string. So on the three uniform hypergraph, we generalize the notion acyclic graph to the hypergraph as follows. Suppose that there are the three integer map U1, U2, U3 from the vertex, such that this satisfies two conditions. The first, for the O vertex V, we have the U1V plus U2V plus U3V equal to 0. And there is the bigger than 0 on the all the edges E1, E2, and E3. Then we can construct on the n copy of this hypergraph an independent set of psi v power n minus small o of n. The idea is similar in the graph scale. We construct the agency tensor of the three uniform hypergraph, and we put on this agency tensor all the diagonal entry equal to 1. Then we take the n power tensor power. Then we consider the subtensor indexed by the uniform n tuple. We can prove the in the subtensor is the identity tensor. Okay, let me stop here. Thanks for listening.
Okay, thank you. Yeah, any questions? So you're constructing corner free sets, but do you think this technique can be used to construct other types of sets which don't contain certain configurations?
Yes. This method can be the constructs for the some configuration for the for example on the L shape, or the other maybe on the box, for example. Yeah. So if the graph has the power structure, we can construct by this method.
Okay, and any more questions? Okay, so let's thank all the speakers in the session. I'll clap for all of you. And you're all welcome to join the following session, which is also the last session. So yeah, I enjoyed my session. So thanks a lot for everybody for speaking and for attending.
Thank you all.